What do you expect from the smallest planet in the solar system? Probably not much. It's a scorched rock. No real atmosphere, no weather systems, no erupting volcanoes, and barely enough gravity to hold on to anything of significance. But that's exactly the problem. Mercury isn't behaving the way it should. Right now, something strange is happening there. Something we genuinely weren't prepared for. New images and detailed data are revealing gases leaking from the planet's surface. Glowing chemical tails are stretching out behind it as it moves through space. And now, for the first time ever recorded in history, scientists have found traces of lithium in Mercury's exosphere. That is not just unusual. By every model we had, it simply doesn't make sense. Why is Mercury, of all the planets, the most beaten, baked, and supposedly inert rock in our solar system, emitting materials it shouldn't even possess? And why are we only seeing this now, in the modern era, with everything we thought we understood already locked in place? Whatever is happening out there, it is no longer quiet. The planet that was supposed to be a textbook example of cosmic finality has suddenly become one of the most confounding objects in the inner solar system. To understand why this is so disorienting, you have to go back and understand what scientists believed for most of modern astronomical history. For decades, genuinely, for most of the 20th century, and well into the 21st, Mercury was treated as the least interesting planet in the solar system. Not ignored exactly, but dismissed, classified, categorized, filed away. The scientific community had developed a coherent, logical, internally consistent story about Mercury, and that story left very little room for surprise. Mercury was small. Mercury was airless. Mercury was scorched to an unimaginable degree on its sun-facing side, and frozen beyond anything hospitable on its dark side. It had no atmosphere in any meaningful sense. It had no weather, no erosion driven by liquid water, and no sign of the kind of geological dynamism that would make it worth monitoring in real time. The basic scientific consensus was extraordinarily simple. Mercury formed from the raw materials of the early solar system. It cooled rapidly due to its small size, and it became a dead rock. That was the story. That was the entirety of the accepted model. Scientists believed that whatever was going to happen on Mercury had already happened billions of years ago, and that the planet since then had simply existed static, silent, and unevolving. A great deal of that assumption came down to size. Mercury is the smallest of the 8 planets, with a diameter of only 4,879 kilometers. That's only marginally larger than our own moon, though Mercury is considerably denser. Small planets, as a rule of physics, lose their internal heat quickly. Their interiors cool faster than larger bodies, because there's less volume generating and retaining that heat relative to the surface area radiating it away. This means that any volcanic or tectonic activity Mercury once had should have ceased very early in its history, perhaps within the first billion years, possibly even sooner. Without internal heat, there's no convection in the mantle, no circulation of molten material, no mechanism to push gases up through the crust and into any kind of atmosphere. Everything should have locked in place. The geological clock on Mercury, most scientists assumed, had stopped a very long time ago. Its proximity to the Sun only seemed to confirm that picture. Mercury orbits at roughly 1/3 the distance from the Sun that Earth does. At perihelion, its closest approach, it's about 46 million kilometers away from the Sun. At aphelion, it swings out to around 70 million kilometers. That elliptical, highly eccentric orbit means the planet is subjected to enormous variation in solar radiation. The surface bakes under an intensity of sunlight that makes even Venus's environment seem moderate by comparison in terms of raw solar input per unit area. For most of scientific history, this proximity was interpreted as a stripping mechanism. A planet that close to the Sun should have had all of its light, volatile materials blasted away or evaporated during formation. What should have remained were the heaviest, most stable elements: iron, nickel, heavy silicates. Mercury was expected to be dense, dry, depleted, and chemically simple on its surface. But there's more to Mercury's orbit than just its distance from the Sun. Its path is the most eccentric of any major planet in the solar system, and also the most inclined relative to the plane in which the other planets orbit. These properties make Mercury's orbit a genuinely strange one, and for a very long time, it was also astronomy's most persistent puzzle. For more than 6 decades, starting in the mid-1800s, astronomers had measured that Mercury's orbit was doing something Newton's laws of gravity couldn't explain. Specifically, the perihelion, the closest point in Mercury's orbit to the Sun, was shifting. It was precessing, rotating slowly around the Sun, advancing by approximately 43 arcseconds per century more than Newtonian mechanics could account for. This was not a tiny discrepancy. Astronomers knew about it, wrote about it, argued about it, and proposed all kinds of explanations, ranging from an undiscovered inner planet to dust rings and various adjustments to the gravitational constant. None of the explanations worked. The problem sat there, unresolved, for decades, a genuine anomaly embedded in the most precise observations of the era. Then, in November of 1915, Albert Einstein published the final, completed version of his general theory of relativity. When he applied it to Mercury's orbit, the precession was explained exactly, not approximately, not as a close fit requiring adjustable parameters, but exactly. The geometry of curved spacetime around a massive object like the Sun produced precisely the orbital shift that astronomers had been measuring for generations. By Einstein's own account, when he realized the calculation matched the observation perfectly, he was beside himself. He described experiencing heart palpitations. It was one of the few moments in the history of theoretical physics where a new framework solved an old mystery with absolute precision on the very first application. That story, Mercury as the proving ground for relativity, became a central piece of its scientific identity. But even that magnificent contribution to our understanding of physics reinforced the broader image of Mercury as an extreme, unusual, largely passive world. A place where interesting things had happened historically, where forces were more powerful than anywhere else in the solar system, but where the planet itself was simply enduring those conditions rather than responding to them in any dynamic way. Mercury's rotation compounded the strangeness of the picture. For a long time, astronomers actually believed Mercury was tidally locked to the Sun, meaning it completed one full rotation for every orbit always showing the same face to the Sun, the way the Moon always shows the same face to Earth. That turned out to be wrong. Mercury actually completes 3 rotations for every 2 orbits, a configuration called a 3-to-2 spin orbit resonance. It still rotates very slowly. One full rotation takes 58.6 Earth days. But because of that resonance, a full solar day on Mercury, measured from one sunrise to the next at any given location, lasts an extraordinary 176 Earth days. This produces one of the most bizarre phenomena in the solar system, around perihelion. When Mercury is closest to the Sun and moving fastest in its orbit, the apparent motion of the Sun, in Mercury's sky, actually reverses. An observer, on the surface near the equator, would watch the Sun rise in the east, slow down, stop, move backward toward the horizon, stop again, and then resume its westward path across the sky. The Sun rises twice in some locations, before setting once. No other major planet in the solar system produces this effect. It's a direct consequence of the interaction between Mercury's orbital speed and its rotational speed, but it's also a reflection of how extreme and unusual every physical parameter on this planet truly is. And then there's the temperature. Because Mercury rotates so slowly, and because it has no atmosphere to retain or redistribute heat, the temperature swings between its day and night sides are the most dramatic of any solid body in the solar system. On the sun-facing side, surface temperatures can climb to approximately 430 degrees Celsius, hot enough to melt lead. On the night side, with no atmospheric blanket to hold any warmth, temperatures plunge to around minus 180 degrees Celsius. That's a swing of over 600 degrees between day and night on the same planet. This also means that the boundary between day and night on Mercury, the Terminator line, is one of the most thermally extreme transition zones in our solar system, moving slowly but inevitably as the planet rotates, leaving the surface alternately baked and frozen with every cycle. The mysteries don't end at the surface. One of the most counterintuitive facts about Mercury is that despite being the closest planet to the Sun, despite having no atmosphere, despite enduring temperatures hot enough to melt metal on its day side, Mercury has ice. Confirmed. Real. Water ice, sitting in permanently shadowed craters near its north and south poles. This was suggested by radar observations in the early 1990s, and confirmed by the Messenger spacecraft, which mapped the planet from orbit between 2011 and 2015. The craters at Mercury's poles are deep enough that their floors never receive direct sunlight. Because Mercury's rotational axis is tilted by less than 1 degree, essentially no tilt at all, these polar shadows are permanent. Temperatures in the deepest crater floors can remain below minus 170 degrees Celsius for billions of years. The ice in those craters isn't just a thin frost. Estimates suggest there are hundreds of billions to potentially 1 trillion tons of water ice locked in Mercury's polar regions, shielded from the sun's radiation by the crater walls, and in some cases, by a thin layer of dark organic material sitting on top of it. That dark layer acts as an insulating blanket, protecting the ice beneath it from sublimating away even during the long polar days when the crater rims receive some oblique sunlight. Finding water ice on the innermost planet was astonishing enough when it was first confirmed. Understanding why it's still there, why it hasn't been lost to the heat or radiation over billions of years, adds another layer of complexity to what we thought was a simple world. Mercury's density adds yet another puzzle. For its size, Mercury is extraordinarily dense, the second densest planet in the solar system after Earth. The reason is its core. Mercury's iron core is enormous relative to the planet's total size, comprising roughly 85% of the planet's radius. By comparison, Earth's core occupies about 55% of Earth's radius. This means that Mercury's rocky mantle and crust are comparatively thin. The planet is essentially a massive iron ball wrapped in a thin shell of rock. How Mercury ended up with such a disproportionately large core is still debated. The leading explanations involve a giant impact early in the solar system's history that stripped away most of Mercury's original rocky outer layers. Or alternatively, the intense solar radiation during formation selectively evaporated lighter materials, leaving the heavy iron to dominate. Neither explanation is fully satisfying, and the precise formation history of Mercury remains an open question. Despite all of this, the strange orbit, the resonant rotation, the polar ice, the oversized core, the dominant scientific consensus for most of modern history was that Mercury was geologically and chemically inert. Whatever geological processes had once shaped it were long finished, and so, accordingly, it received far less attention than the other planets. Mars had liquid water in its past, potential for life, and ongoing geological processes. Venus had a thick atmosphere and runaway greenhouse dynamics. Jupiter and Saturn had complex systems of moons and powerful storm systems that had been active for centuries. Even the outer ice giants, Uranus and Neptune, had atmospheric dynamics worth monitoring. Mercury was just sitting there. Mariner 10, the first spacecraft to visit Mercury, flew past the planet 3 times between 1974 and 1975. The images it returned showed a cratered surface that looked, at first pass, reassuringly similar to the moon. Impact craters of various sizes, ancient lava plains, long cliff-like scarps, called lobate scarps, that were formed when the planet contracted as its core cooled. The surface was old. The features were ancient. There were no obvious signs of active processes, no fresh volcanic flows, nothing that suggested Mercury was still doing anything geologically meaningful. Mariner 10 confirmed the old picture rather than challenging it, and for more than 3 decades after that mission, Mercury remained in the background of planetary science. The assumption that Mercury was a reference point for geological death became so embedded in the field that it shaped not just how Mercury was studied, but how other planets and exoplanets were analyzed. Scientists would use Mercury as an endpoint in their thinking. If a planet is small and close to its star, it will end up like Mercury. That was the model. It influenced how astronomers thought about planetary habitability, about the lifespan of atmospheric processes, about the fates of small rocky worlds. That's why everything happening now is so jarring. The discoveries being made in the current era aren't just refinements of existing knowledge. They're not filling in small gaps or correcting minor errors at the margins. They're directly contradicting the foundational assumptions that defined how Mercury was understood for most of modern history. Scientists didn't expect Mercury to be releasing material into space at a detectable rate. They didn't expect new elements to be discovered in its vicinity. They didn't expect to be monitoring a dynamic, ongoing process with a spacecraft specially equipped to track the details in real time. And yet here we are. Mercury is shedding material. It is emitting atoms into space. It has a chemical tail. It has lithium, where lithium was not expected. And it turns out it was doing all of this long before we had the technology sophisticated enough to detect it properly. The planet we wrote off as a dead world has been quietly active the entire time, operating through processes we didn't fully appreciate, processes that become more remarkable the closer you look at them. This is where everything changes. This is the point at which the old model breaks and the new picture begins to take shape. Mercury doesn't have an atmosphere. That fact is solid, well established, and not in dispute. But it does have something thinner, more tenuous, and in many ways more interesting than a conventional atmosphere. It's called an exosphere, not a gas blanket in the way Earth has one, not a dense layer of molecules that create pressure and weather and all the atmospheric phenomena we associate with living planets. An exosphere is something far more fragile, a sparse, near vacuum zone where individual atoms and molecules exist in such low concentrations that they rarely, if ever, collide with each other. They bounce around. They arc through space on ballistic trajectories, sometimes falling back to the surface, sometimes gaining enough velocity to escape the planet's gravity entirely and stream off into the solar wind. Mercury's exosphere is constantly being generated and constantly being destroyed. Atoms enter it from the surface through several mechanisms, hang in the near vacuum above the planet for some period ranging from minutes to hours, depending on their energy and trajectory, and then either fall back or escape. It is not a stable, self-sustaining system. It's a dynamic, perpetually renewed, perpetually leaking envelope of material. And somehow, impossibly, by the standards of the old model, it contains elements Mercury shouldn't still have. The first one that attracted serious scientific attention was sodium. Sodium is a relatively light element, chemically reactive under Earth conditions, but in its atomic form in space, it has a useful property. It glows under ultraviolet light. Sodium atoms absorb photons from the sun and re-emit them in a characteristic yellow-orange color that can be detected by instruments on Earth and in space. In the late 1980s and early 1990s, astronomers using ground-based telescopes began detecting sodium emissions from Mercury's vicinity. Not just traces of it near the surface, but sodium streaming away from the planet in a long, faint tail, extending tens of thousands of kilometers into space, and, in some observations, stretching to hundreds of thousands or even millions of kilometers. The sodium tail is real, measurable, and persistent. It follows Mercury as it moves through its orbit, pushed away from the sun by solar radiation pressure. The same force that drives comet tails away from the sun regardless of the comet's direction of travel. Mercury's sodium tail doesn't look like a comet's tail. It's thinner, less dramatic, visible only with the right instruments tuned to the right wavelengths. But it's structurally similar in some ways. Material is leaving the planet's surface, entering the exosphere, and then being pushed away by sunlight faster than Mercury's weak gravity can recapture it. What made sodium particularly puzzling was the quantity. There was more of it than the early models suggested there should be. Given Mercury's proximity to the sun and the age of the solar system, the expectation was that sodium and other light, volatile materials should have been depleted from Mercury's surface long ago. The sun's radiation and solar wind should have stripped them away over billions of years, leaving a sodium-depleted surface behind. Instead, the sodium tail was not only present, but appeared consistently, orbit after orbit, year after year. Something was replenishing the supply, or the reservoir was far larger than anyone had accounted for. Then potassium was detected. Potassium is heavier than sodium and less abundant in Mercury's exosphere, but it's there. Ground-based spectroscopy picked it up, and more detailed measurements confirmed a potassium tail extending behind the planet, though not stretching as far as the sodium tail. Potassium's detection was less surprising in isolation. It belongs to the same family of elements as sodium and shares similar chemical behavior. But together, sodium and potassium presented a clear pattern. Mercury was actively losing material from its surface at a rate that was ongoing and measurable. This wasn't a relic of ancient processes. It was happening now, in the present day, at a rate high enough to produce visible, trackable chemical tails in space. The Messenger mission, which entered orbit around Mercury in 2011 and operated until 2015, transformed our understanding of the exosphere. Messenger carried instruments specifically designed to analyze the composition of Mercury's surface and the particles in its immediate environment. It found sodium and potassium as expected, but it also found a broader range of elements than previous observations had captured. Calcium, magnesium, sulfur, and others were detected in the exosphere. The picture that emerged was not of a simple, depleted, chemically straightforward surface, but of a complex mixture of materials with a surprisingly rich, volatile component elements that should not have been abundant on a planet this close to the sun, yet were clearly present and clearly escaping. Messenger also revealed something important about how the exosphere varies. The density of sodium, for example, changes significantly depending on where Mercury is in its orbit. When Mercury is closer to the sun, at perihelion, solar radiation pressure and solar wind intensity both increase. The rate at which atoms are knocked off the surface increases accordingly. The sodium tail becomes denser, longer, more detectable. At aphelion, further from the sun, the tail thins out. This variability was a critical clue. It meant the exosphere was not a static relic, but an actively driven system, responding to changes in the solar environment in real time. The sun was doing something to Mercury, and Mercury was responding. And then came lithium. This is the discovery that genuinely upended expectations. Lithium is a light element, the third lightest on the periodic table, after hydrogen and helium. It is not commonly detected in the exospheres of rocky planets, and there was no strong theoretical reason to expect it at Mercury in significant quantities. The models of Mercury's surface composition, based on what was understood about how rocky planets form in the inner solar system, did not predict lithium as a major component. When scientists began finding evidence of lithium in Mercury's exosphere in recent data, particularly in observations linked to the BepiColombo mission's flybys, the reaction in the scientific community was something close to disbelief. It wasn't a noisy, dramatic announcement. It was a quiet realization buried in spectrographic data, the kind of detection that requires careful cross-referencing and instrument calibration before anyone is willing to commit to it publicly. But once confirmed, the implications were immediate and significant. Lithium is volatile enough that it should have been among the first elements depleted from Mercury's surface over billions of years of intense solar radiation. If it's still escaping now, if it's still present in Mercury's outer environment in detectable quantities, then either Mercury's surface contains far more lithium than the models predicted, or the mechanisms through which Mercury retains and then releases volatile materials are more efficient and complex than previously understood. The lithium detection also opens a broader question. If lithium is there, and we missed it, what else is there that we've missed? The exosphere of Mercury is not easy to study in detail. Ground-based observations are limited in spectral coverage and sensitivity. MESSENGER was a pioneering mission, but it operated for a relatively short time, and its instruments, as sophisticated as they were for their era, had limits. The full compositional inventory of Mercury's exosphere is almost certainly not complete. What else is escaping from that surface? What other volatile elements are sitting in Mercury's crust in quantities no one expected? These are not rhetorical questions. They're the scientific agenda driving current research, and they're the reason the BepiColombo mission, currently in the final stages of its journey to Mercury, represents such an important opportunity. BepiColombo is a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency. It launched in 2018 and has been conducting flyby maneuvers to slow itself into a capture orbit around Mercury, a notoriously difficult navigational challenge given how much energy a spacecraft needs to shed to enter orbit around the innermost planet. 6 flyby passes were completed, and the spacecraft is now on the final leg of its approach to orbit insertion. What makes BepiColombo particularly relevant to the current moment in Mercury science is that it was designed with the exosphere in mind. MESSENGER revealed that the exosphere was more complex and more dynamic than expected, but it left a long list of questions it couldn't answer. BepiColombo carries a suite of instruments specifically calibrated to address those questions. It has sensors tuned to detect individual atoms escaping from the surface, to characterize their energy states, to track their trajectories, and to map the spatial distribution of different elements across Mercury's surface and immediate environment. It has an imaging spectrometer that can analyze sunlight reflected off and emitted from the planet at wavelengths covering a broader range than any previous Mercury instrument. And it has a thermal mapper that can connect surface temperature patterns, which vary enormously across Mercury's surface because of its extreme temperature swings, to the rate of particle release. The timing is not incidental. The lithium detection came in part from data collected during BepiColombo's flyby passes, which gave scientists their first look at Mercury through BepiColombo's instruments, even before the spacecraft reaches its final orbit. Those flybys confirmed that the instruments work as designed, that they're sensitive enough to detect trace elements in the exosphere, and that they're seeing things MESSENGER couldn't resolve. The full science mission, once BepiColombo settles into orbit, will allow for systematic mapping of the exosphere over time, tracking how it changes with Mercury's position in its orbit, how it responds to solar flares and other changes in solar activity, and whether there are localized source regions on the surface where volatile release is more concentrated. This last point is particularly important. The mechanisms by which atoms leave Mercury's surface and enter the exosphere are not uniform. Different processes dominate in different locations, at different times of day, and at different points in Mercury's orbit. Understanding which mechanisms are most important and where they're most active requires the kind of repeated, detailed observations that only a spacecraft in orbit can provide. The mechanisms themselves are worth understanding in depth because they reveal something surprising. Mercury doesn't need to be geologically active to be releasing material. It doesn't need volcanoes, or fresh lava flows, or interior heat driving gases through the crust. The processes happening on Mercury's surface right now are driven entirely by external energy coming in from space, not energy generated within the planet itself, and they're sufficient to explain everything we're observing in the exosphere. The first, and arguably most energetic of these mechanisms, is micrometeorite bombardment. Mercury is not well protected. It has no atmosphere to act as a shield, burning up incoming particles before they reach the surface the way Earth's atmosphere destroys most meteors. It has a magnetic field, and this was another major surprise that Messenger confirmed, because Mercury was not expected to have a significant magnetic field, given its size and the assumption that its core was cool and solid, but that field is weak, far too weak, to deflect small incoming particles, the way Earth's magnetosphere deflects the solar wind. So Mercury's surface is continuously being struck by tiny particles, micrometeorites ranging from microscopic dust grains to small pebbles, traveling at tens of kilometers per second. When these particles hit the surface, the collision releases energy instantaneously and locally. The impact vaporizes both the incoming particle and a small amount of the surface material immediately beneath it. Temperatures in the microscopic impact zone spike for a fraction of a second to thousands of degrees, causing the local material to flash into a vapor of individual atoms. Those atoms expand outward from the impact point. Most of them fall back to the surface almost immediately, but some gain enough velocity from the impact to escape Mercury's gravity, particularly if they were near the surface to begin with and were loosely bound in the mineral structure. Over billions of years, the cumulative effect of this constant micrometeorite rain has been to process the uppermost layer of Mercury's surface repeatedly, mixing it, fracturing it, and sending a steady trickle of atoms into the exosphere. The second mechanism is solar wind sputtering. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun at speeds of hundreds of kilometers per second. At Earth, the magnetosphere deflects most of this flow around the planet. At Mercury, the weaker magnetic field offers less protection, and significant portions of the solar wind interact directly with the surface, particularly at the poles and in regions where the magnetic field lines connect directly to the surface rather than deflecting the flow around the planet. When a high-energy solar wind particle strikes the surface, it transfers momentum to the surface atoms. If that transfer gives a surface atom enough energy, the atom is ejected, sputtered off the surface, and enters the exosphere. This process is most effective for light, loosely bound atoms. Sodium and potassium are prime candidates, which is one reason they're so prominent in Mercury's exosphere. But sputtering can dislodge a wide range of surface materials, depending on the energy of the incoming particle and the binding energy of the surface atom. Solar wind sputtering has an additional feedback effect. When the sun is more active during solar storms, coronal mass ejections, or periods of elevated solar wind density, the sputtering rate increases. More particles hitting Mercury's surface means more atoms being knocked loose, which means a denser exosphere and a more prominent chemical tail. This explains some of the variability that Messenger detected in the sodium exosphere, and it's one of the dynamics BepiColombo is specifically designed to monitor in real time. Correlating changes in solar wind intensity with changes in the exosphere's density will help scientists establish exactly how much of Mercury's material loss is driven by this mechanism versus the others. The third mechanism is photon-stimulated desorption, sometimes called photodesorption. This is driven by ultraviolet photons from the sun rather than by particles. When a UV photon of sufficient energy strikes a surface atom, it can break the chemical bond holding that atom to the mineral surface below it. The atom is effectively lifted free by the energy of the photon and enters the exosphere. This mechanism is most effective for certain surface compositions, in particular, for minerals that contain sodium and potassium compounds, which are relatively easy to photodesorb. It's also most effective on the sun-facing side of Mercury, in the areas receiving the most direct ultraviolet radiation. And it's been happening continuously since Mercury formed, which means it's one of the primary reasons the sodium tail is so consistent and so well established, despite the billions of years of material loss implies. The fourth mechanism is thermal desorption. Mercury's temperature swings are among the most extreme in the solar system, and those swings have consequences at the molecular level. As the surface temperature rises from the deep cold of the Mercurian night toward the searing heat of the Mercurian day, atoms near the surface gain thermal energy. For atoms that are only weakly chemically bound to the surface mineral they sit in, this thermal energy can be sufficient to break the bond and allow the atom to escape. The effect is most pronounced in the equatorial regions, where sunlight is most direct and temperatures are highest. Over time, the repeated cycling of heating and cooling does additional work. It causes minerals to expand and contract, developing microfractures, breaking apart crystal structures, and exposing fresh mineral surfaces that haven't been processed yet. This slow mechanical churning of the uppermost layer of Mercury's surface soil, called regolith, has been termed thermal gardening, and it continuously brings new material to the surface, where the other escape mechanisms can act on it. What makes all of these mechanisms work together so effectively is the nature of Mercury's surface chemistry. Mercury's surface is not simply iron and rock. Messenger revealed that the surface contains significant volatile component minerals that incorporate sodium, potassium, sulfur, and other elements that are loosely bound at the molecular level and relatively easy to liberate. These volatile-bearing minerals don't require extraordinary conditions to break apart. They're sensitive to solar radiation, thermal stress, and particle bombardment in ways that more refractory, tightly bound minerals are not. This is why the escape mechanisms don't need to be extreme to be effective. The material is already there, already near the surface, already loosely held, just waiting for a photon or a micrometeorite or a solar wind proton to provide the final push. Mercury's low gravity compounds the effect. Compared to Earth, Mars, or Venus, Mercury's gravitational pull at its surface is weak. An atom that receives enough energy to lift off from the surface doesn't need to travel very far or very fast to escape entirely. Once it reaches the exosphere, there's no atmospheric drag to slow it down, no dense gas layer to scatter it back toward the surface, and the weak gravity means escape velocity is relatively low. Atoms that have been photodesorbed or thermally released or sputtered find it comparatively easy to leave for good. This is why the sodium and potassium tails can stretch for such enormous distances behind the planet. Once those atoms are moving in the right direction, with enough velocity, Mercury has very little ability to reclaim them. Together, these four mechanisms, micrometeorite bombardment, solar wind sputtering, photon-stimulated desorption, and thermal desorption, create a system that is continuously, actively, and measurably releasing material from Mercury's surface into space. And critically, none of these mechanisms requires any internal heat, any geological activity, or any process happening within the planet. They are all externally driven, powered by the sun and by the flux of particles moving through the inner solar system. This means they haven't stopped. They haven't slowed down in any fundamental sense. They're happening right now, at the same rate they've been happening for billions of years, driven by external inputs that haven't changed in any significant way over geological timescales. The emissions we're detecting in Mercury's exosphere are not echoes of a more active past. They're not the fading remnants of a planet that once had volcanoes and is now cooling toward true inertness. They are the present-day output of a system that is still fully functional quiet in a geological sense, yes, but chemically and physically active at the surface level in ways that are real, measurable, and ongoing. Mercury is still shedding. It was always shedding. We just didn't have the instruments to see it clearly enough until relatively recently, and even now the picture is still coming into focus. This distinction matters. It changes the scientific classification of Mercury in a fundamental way. A truly dead world has no ongoing processes of any kind at its surface or interior. Mercury is not that. Mercury is a world where the interior has indeed cooled and quieted. No active volcanism, no tectonic activity, no fresh magma pushing toward the surface. But the surface and near-surface environment is anything but static. It is continuously bombarded, continuously irradiated, continuously losing material to space. The planet is eroding, slowly but measurably, and the products of that erosion are detectable from Earth and from space. What this means for the longer-term evolution of Mercury is an open question. Over billions more years, does Mercury continue to lose volatile material from its surface until none is left? Does the exosphere thin further as the volatile reservoir is depleted? Or are there deeper sources, perhaps volatile compounds locked in the lower crust, that the surface processes are slowly exposing and tapping? These are questions that require data we don't yet have. But BepiColombo's arrival in Mercury orbit will help address them, providing the first long baseline, high-sensitivity monitoring of how the exosphere changes over time. There is something deeply uncomfortable about realizing that a scientific consensus you've held for decades is wrong. Not wrong at the margins, not slightly miscalibrated, but wrong in a way that changes the fundamental picture. That's the position Mercury science is in right now. The planet wasn't just misunderstood in minor ways. The entire framework through which scientists interpreted it, the dead world model, the chemically inert surface, the idea that everything interesting about Mercury was ancient history, that framework is being dismantled piece by piece as new data comes in. And the dismantling didn't happen all at once. It happened gradually, instrument by instrument, detection by detection, over the course of several decades. Each new measurement added something that didn't fit. Each new observation required a small revision to the model. And then the revisions accumulated into something that couldn't be ignored, a body of evidence pointing clearly to the conclusion that Mercury is more active, more chemically complex, and more dynamic than any serious model from the 20th century predicted. To understand what the data is actually showing, you have to spend some time with the exosphere, not just as a concept, but as a physical reality. Because the exosphere of Mercury is where all of the most surprising modern discoveries are being made, and because the way it works tells you something profound about the difference between a dead planet and a dynamically active surface. Imagine standing on Mercury's surface. You're somewhere in the mid-latitudes on the day side, maybe mid-morning in Mercurian terms, which means sunlight has been hitting this spot for the equivalent of several Earth weeks. The surface beneath your feet is dark, fine-grained regolith, a deep layer of powdery, fragmented rock built up over billions of years of micrometeorite impacts. It looks superficially like the lunar surface, the same kind of space-weathered, pulverized material that forms the top layer of any atmosphere-free rocky body in the inner solar system. But if you could analyze it chemically, you'd find it's not as simple as it appears. Mixed into that dark powder are minerals containing sodium compounds, potassium compounds, sulfur-bearing phases, and now we know, materials containing lithium. These are volatile elements and compounds that respond readily to the intense radiation and particle bombardment coming from the nearby sun. Above your head, if Mercury had a visible sky, which it doesn't in any conventional sense, there is essentially nothing. The vacuum is almost perfect, but not quite. In that near vacuum, a sparse, invisible population of individual atoms is moving. Some of them were knocked off the surface just seconds ago by micrometeorite impacts or solar wind particles. Some of them absorbed a photon and were lifted free of their mineral bonds moments before. Some of them were thermally shaken loose from the surface during the slow, grinding temperature rise of the Mercurian morning. They're moving in all directions, most of them in arcing trajectories that will carry them a few hundred meters or a few kilometers before Mercury's gravity curves them back toward the surface. But some of them, the ones moving fast enough, are on escape trajectories. They will never come back. The atoms that escape don't immediately form a tail. First, they enter the exosphere proper, moving outward from the planet, while solar radiation continues to act on them. The sodium atoms, in particular, are susceptible to a secondary process. The photons they absorb give them momentum in the direction away from the sun. This radiation pressure, the same force that pushes comet tails away from the sun, regardless of the comet's direction of travel, gradually redirects the escaping sodium atoms into a stream flowing away from the sunward side of the planet. Over time, this stream builds up into the extended sodium tail that has been detected from Earth, a faint but measurable structure extending behind Mercury as it moves through its orbit. What makes the exosphere particularly interesting scientifically is not just its composition, but its variability. It is not a fixed, stable system. It fluctuates on timescales, ranging from hours to months, responding to changes in solar activity, changes in Mercury's distance from the sun, and even changes in the local surface chemistry as different terrain types rotate into and out of the sun-facing hemisphere. One of the most striking examples of this variability involves the relationship between Mercury's orbit and the sodium tail. Messenger data showed clearly that the sodium tail is most prominent and most extended when Mercury is near perihelion, its closest approach to the sun. This makes intuitive sense once you understand the mechanisms. At perihelion, solar radiation intensity is at its maximum. Photodesorption rates are highest. Solar wind flux is at its peak. The bombardment rate from any interplanetary dust concentrated near the sun's inner solar system is elevated. All of these factors combine to maximize the rate at which sodium atoms are released from the surface and pushed away by radiation pressure. The tail can extend for several 100,000 kilometers at perihelion, perhaps more. At aphelion, the opposite applies. The sun is more distant, its radiation weaker, its wind less dense, the release rate drops, the tail becomes thinner and shorter. From Earth, It becomes harder to detect, but it doesn't disappear. The mechanisms that drive sodium loss from Mercury's surface are external and continuous. There's no season on Mercury where the sun goes away entirely, no period of rest during which the surface can accumulate material undisturbed. Even at aphelion, the sun is still delivering ultraviolet radiation and solar wind particles, and the exosphere is still being generated and still escaping. The potassium component of the exosphere follows a similar pattern, though with lower abundances and somewhat different spatial distribution. Potassium is heavier than sodium, which means its thermal desorption rate is slightly lower, and it requires somewhat more energy to escape from surface minerals. The potassium tail is consistently shorter than the sodium tail, and requires more sensitive instrumentation to detect. But it's there, and its presence is significant. Sodium and potassium are both alkali metals. They belong to the same chemical family. They behave similarly under the conditions on Mercury's surface, and their co-presence in the exosphere confirms that Mercury's surface minerals contain a broader inventory of volatile alkali elements than was expected from standard models of inner solar system planetary formation. The calcium detection was, in some ways, even more surprising than the potassium. Calcium is not an alkali metal. It belongs to the alkaline earth group, a different family of elements with different chemical properties. It's heavier than sodium and potassium, and it's bound more tightly in most common surface minerals. Under standard photodesorption conditions, calcium shouldn't be particularly easy to liberate. Yet MESSENGER detected calcium in Mercury's exosphere, and in amounts that were difficult to explain with the standard exosphere models. The calcium detection forced scientists to revisit their models of how the exosphere is generated, and it pointed toward micrometeorite impact vaporization as a more significant mechanism than had been assumed. Calcium's presence in the exosphere is now primarily explained by the vaporization of calcium-bearing minerals during impacts. The flash of heat at the point of impact liberates calcium atoms that wouldn't have been easily released by photons alone. Magnesium was another detection that expanded the picture. Magnesium is a major component of many common rock-forming minerals, including pyroxenes and olivines, which are among the most abundant minerals on the surfaces of rocky planets. Its presence in Mercury's exosphere isn't shocking in the same way lithium's is, but the quantities detected and the spatial distribution of magnesium emissions provided important information about which surface minerals are contributing to the exosphere and through what mechanisms. Magnesium's release is particularly sensitive to micrometeorite impacts, and MESSENGER data showed that magnesium concentrations in the exosphere were highest on the hemisphere most exposed to the incoming flux of interplanetary dust. Sulfur was detected at Mercury's surface by MESSENGER in amounts that genuinely surprised planetary scientists. Sulfur is highly volatile. It combines readily with other elements. It evaporates at relatively low temperatures, and it's generally not expected to be abundant on the surface of a planet that spent billions of years being intensely irradiated and heated. Yet Mercury's surface showed elevated sulfur concentrations that couldn't be explained by the incoming flux of sulfur-bearing meteorites alone. Some of that sulfur must have originated from within Mercury itself, perhaps released by ancient volcanic activity and incorporated into surface minerals that have since been slowly processed by surface weathering and micrometeorite. Bombardment. Whether sulfur is detectable in Mercury's exosphere in significant quantities is something BepiColombo is equipped to determine, with greater sensitivity than was available to MESSENGER. And then there is lithium, the element whose detection in Mercury's exosphere has generated the most excitement and the most uncertainty. Lithium sits at atomic number 3 on the periodic table, just above hydrogen and helium, and below sodium and potassium in the same chemical family. It's the lightest solid element, the least dense metal known. In the solar system, lithium was produced primarily in the Big Bang and through cosmic ray interactions with other elements, and its cosmic abundance is relatively low. On rocky planets, lithium is present in trace quantities in many minerals, but it's not a major constituent of the bulk composition of any planet we know of. The fact that lithium is escaping from Mercury's surface in quantities detectable by the instruments aboard BepiColombo suggests that there is more lithium at or near Mercury's surface than standard planetary formation models account for. Where did it come from? There are several possibilities, and right now, none of them is definitively confirmed. One possibility is that Mercury's surface has been enriched in lithium by the continuous bombardment of micrometeorites over billions of years. Many meteoritic materials contain lithium, and their vaporization upon impact deposits lithium atoms into the surface regolith. Another possibility is that Mercury's unusual formation history, the giant impact or thermal stripping events that may have given it its oversized iron core, also resulted in a surface composition that retained more light. Volatile elements than standard models predict, perhaps concentrated in specific mineral phases. A third possibility, and one that some researchers find particularly compelling, is that Mercury's volcanic history played a role. Although active volcanism on Mercury ended long ago, it may have been more recent and more extensive than previously thought. Messenger found evidence of explosive volcanic activity in the form of pyroclastic deposits, remnants of gas-rich eruptions that flung material across the surface that appear to be relatively young in geological terms, dating to perhaps within the last billion years or so. If Mercury had an extended period of volcanic activity that produced gases, including lithium-bearing compounds, those gases could have been incorporated into surface minerals and are now being slowly released by the ongoing surface processes. The honest answer is that the lithium detection raises more questions than it answers. That's not a criticism of the science, it's the nature of discovery. When you find something unexpected, the immediate response shouldn't be to force it into the existing model. It should be to interrogate the model itself, to ask what assumptions led to the prediction of lithium's absence, and to determine which of those assumptions needs to be revised. Mercury is now forcing that interrogation at multiple levels simultaneously, and the answers will take years to fully work out. What we can say with confidence is this: Mercury's surface is chemically richer than the old models predicted. It contains a broader range of volatile elements, present in higher quantities, than the standard story of inner solar system planetary formation suggested should be possible for a planet so close to the Sun. This either means that the formation models need revision, or that Mercury's evolutionary history, the specific events and processes that shaped it from a newly formed planet into its current state, was significantly different from what was assumed. Either conclusion has implications that extend far beyond Mercury itself. The magnetic field deserves its own moment of attention because it was one of the most dramatic surprises in the entire history of Mercury exploration, and because it's directly connected to how the exosphere behaves and how material escapes from the planet's surface. When Mariner 10 flew past Mercury in the 1970s, it detected something that shouldn't have been there: a global magnetic field. Not a strong one. Mercury's field is roughly 100 times weaker than Earth's, but unmistakably global, unmistakably dipolar, and unmistakably generated by some kind of internal dynamo process. This was astonishing. The standard model of planetary magnetic fields held that they required a large, liquid, conducting core, the kind of core that generates a dynamo through the convective motion of electrically conducting material. Earth has this, and so does the outer solar system's largest planets. But Mercury? Mercury was too small and too old. Its core should have solidified billions of years ago, ending any dynamo action long before Mariner 10 arrived. The detection forced a fundamental rethinking of what Mercury's interior was like. If it had a magnetic field generated by an internal dynamo, at least part of its core had to still be liquid. But how? How had Mercury's core retained enough heat to remain partially molten after 4.5 billion years? Several mechanisms have been proposed. One involves the presence of light elements in the core materials like sulfur that lower the melting point of the iron-nickel alloy and allow it to remain liquid at lower temperatures and over longer timescales than pure iron-nickel would. Another involves the stratification of Mercury's core, with a solid inner core and a liquid outer shell, with convection in that outer shell being the engine for the dynamo. Messenger's gravity measurements and observations of Mercury's rotation over its mission lifetime helped confirm that at least the outer part of Mercury's core is indeed liquid. The planet wobbles in a way that is only consistent with a fluid outer core, not a fully solid one. So Mercury's magnetic field is real. It is being maintained today by an active, ongoing dynamo process, and its existence is one of the strongest pieces of evidence against the fully dead planet model. But Mercury's magnetic field, while real, is unusual in ways that go beyond its weakness. Messenger discovered that the magnetic dipole is offset from the planet's center of mass. It's shifted northward by about 20% of Mercury's radius. This asymmetric configuration means that the magnetic field is stronger over the northern hemisphere than the southern hemisphere. The practical consequence is that solar wind particles have easier access to the southern hemisphere, where the magnetic field is weakest. This creates an asymmetry in the exosphere. Solar wind sputtering is more intense in the south, which means more surface material is being knocked loose there than in the north. BepiColombo's instruments, with their higher sensitivity and ability to monitor the same regions over extended periods, should be able to map this asymmetry in detail for the first time. The magnetic field also mediates the way solar wind energy is transferred to Mercury's surface in a process called magnetic reconnection. When the solar wind carries its own magnetic field, which it does, as part of the larger heliospheric magnetic field, and that field encounters Mercury's magnetic field, the two fields can connect and merge under certain conditions. When this happens, energy is released, and charged particles are accelerated along the reconnected field lines directly into Mercury's surface. These events, called flux transfer events, are known to occur at Earth's magnetopause as well, but at Earth, they mostly deliver energy to the upper atmosphere. At Mercury, with no real atmosphere to absorb and redistribute that energy, the particles hit the surface directly. This adds another intermittent, but potentially intense source of surface sputtering to the list of mechanisms generating the exosphere. Messenger detected evidence of these flux transfer events at Mercury, and they were more frequent and more energetic than expected. Some of them may be significant contributors to the exosphere, particularly in concentrated bursts following solar storm activity. If BepiColombo can catch Mercury in the middle of or immediately after a solar storm, watching in real time how the exosphere responds to the elevated particle bombardment, that would provide invaluable data on how much of the total material loss from Mercury's surface is driven by these episodic, intense events versus the background continuous processes. The magnetic field also interacts with Mercury's exosphere in a way that has no real parallel at Earth. Some of the ions generated in the exosphere atoms that have been ionized by solar UV radiation can be captured by the magnetic field and recycled back toward the surface. This creates a partial recycling loop in which some fraction of the material that escapes the surface is returned to it, reprocessed, and released again. The dynamics of this ion recycling are complex and not fully understood, and they're one of the areas where BepiColombo's particle detectors and field instruments will be particularly valuable. Understanding the magnetic field and how it shapes the exosphere isn't just important for Mercury. It's important for the growing catalog of exoplanets that are known or suspected to have magnetic fields. Many of the rocky planets being detected around other stars, particularly those in close orbits around their host stars, may have magnetic fields that interact with their star's wind in ways similar to how Mercury's field interacts with the solar wind. Mercury provides a nearby, accessible example of this interaction in its most extreme form. Every piece of data BepiColombo collects about how Mercury's magnetic field shapes its surface environment is a data point that can be applied to understanding exoplanetary environments that we will never be able to visit directly. There's another piece of the Mercury puzzle that gets less attention than the exosphere or the magnetic field, but that is, in many ways, equally surprising: the shrinkage. Mercury is getting smaller. Not quickly, not in any way that would be noticeable on a human timescale, but measurably, demonstrably, and continuously, the planet is contracting as its enormous iron core slowly cools. The evidence for this is written across Mercury's surface in the form of landforms called lobate scarps, long, sinuous cliffs that cut across the landscape, sometimes extending for hundreds of kilometers. These scarps are thrust faults, formed when two sections of Mercury's crust were compressed against each other as the interior shrank and the surface buckled. They are, in essence, the wrinkle lines of a drying apple, the surface creasing and folding as the interior loses volume. Mariner 10 saw some of these scarps in the portion of Mercury's surface it managed to image, which was about 45% of the total. Messenger mapped the entire surface and found lobate scarps everywhere, not just in the areas Mariner 10 had photographed, but distributed globally in a pattern consistent with the planet undergoing uniform global contraction rather than localized tectonic stress. The estimated total reduction in Mercury's radius since the planet's surface solidified is somewhere between 7 and 10 kilometers. That might not sound dramatic, but it represents a significant fraction of the planet's total radius and a truly enormous displacement of crustal material. What's particularly interesting is that some of these scarps appear to be geologically young by planetary science standards, meaning they formed within the last few 100 million years rather than billions of years ago. Messenger found scarps that cut across impact craters of estimated age in the hundreds of millions of years, which means the thrust faulting that created those scarps had to have occurred after those craters formed. This is direct evidence that Mercury's interior is still cooling, and its surface is still contracting in geological timescales, not just in the early solar system. The contraction also affects the interior in ways that may have implications for the exosphere. As the core cools and contracts, it creates stresses in the overlying mantle and crust. These stresses, even if they're insufficient to drive full volcanic eruptions today, may be sufficient to create pathways through the crust microfractures and fault zones through which gases trapped in the mantle or crust can migrate upward and reach the surface. The amounts released by this mechanism would be small compared to the surface processes discussed earlier, but they might contribute trace quantities of specific elements to the exosphere that would otherwise be absent. Whether any of the exotic elements detected in Mercury's exosphere have an interior source rather than a surface source is something that current data cannot definitively resolve, and that's another reason BepiColombo's observations are so eagerly anticipated. The shrinkage also connects to the pole ice in an unexpected way. As Mercury's surface is deformed by contraction, the geometry of polar crater floors can change very subtly over geological time. A crater that was once partially exposed to oblique sunlight might become more fully shadowed as the terrain around it deforms. A crater that was previously in shadow might become less so. These changes happen very slowly, but over hundreds of millions of years, they alter the thermal environment at the poles in ways that affect the stability of the water ice. Some ice deposits may have been emplaced relatively recently, geologically speaking, in craters that became permanently shadowed only after contraction events created new shadowing geometries. Others may have been exposed and lost as the terrain evolved. The origin of the polar ice is itself an unresolved question. Water doesn't form naturally on Mercury's surface in significant quantities. There's no internal liquid water, no hydrothermal activity, and no condensation from an atmosphere. The water that's sitting frozen in Mercury's polar craters had to have been delivered there from outside. The most likely sources are comet impacts and water-bearing asteroid impacts, events that delivered water to Mercury's surface, with most of it evaporating quickly under the solar radiation, but a small fraction landing or drifting to the polar regions, where it could survive in permanent shadow. Alternatively, the water might have been delivered in a more diffuse way through the slow accumulation of water molecules from the solar wind protons that combine with oxygen and surface minerals to form water, which then migrates across the surface toward the cooler polar regions. The dark, organic-rich layer sitting on top of the polar ice adds another dimension of complexity. Messenger detected this layer in reflectance data. The ice beneath was less reflective than pure water ice, and modeling indicated that a thin layer of darker material was covering it. The most likely explanation is that this layer consists of complex organic compounds that were delivered along with the water by comets or asteroids, or that formed in situ through irradiation of simpler carbon and hydrogen compounds. This means that Mercury's poles contain not just water ice, but a record of the organic chemistry that was prevalent in the early solar system. The kinds of molecules that might be present in that dark layer, precursors to amino acids, complex hydrocarbons, possible prebiotic compounds, are of scientific interest, far beyond what they tell us about Mercury specifically. Messenger's legacy deserves careful consideration here, both for what it achieved and for what it left unfinished. The mission was a triumph of planetary exploration. Entering orbit around Mercury is an extraordinary navigational challenge. The planet's proximity to the Sun means a spacecraft approaching it has to shed enormous amounts of orbital energy to slow down enough to be captured. Messenger's engineers used a series of planetary flyby maneuvers, using Venus and Mercury itself as gravitational brakes, over several years of cruise before finally entering orbit in March 2011. It operated in orbit for 4 years, mapping the entire surface, measuring the magnetic field, sampling the exosphere, and analyzing surface composition through a suite of spectrometers. The data Messenger returned transformed Mercury from a largely unknown world into a complex, fascinating, and deeply surprising planet. Almost every major finding was unexpected to some degree. The crustal sodium and potassium abundances were higher than predicted. The sulfur content was far higher than expected for a planet formed so close to the Sun. The carbon detected at the surface, in amounts suggesting that much of the surface darkening traditionally attributed to space weathering, might actually be due to carbon delivery from comets, and carbon-rich asteroids was a complete surprise. The evidence for recent geological activity in the form of young scarps and young pyroclastic deposits pushed the timeline for Mercury's geological activity billions of years closer to the present than anyone had anticipated. But Messenger's orbit was not ideal for all measurements. Its highly elliptical orbit took it from very low altitudes over the northern hemisphere to much higher altitudes over the south. This geometry, a consequence of the orbital mechanics used to reach Mercury with the available fuel, meant that MESSENGER's surface chemistry measurements and exosphere sampling had uneven coverage. The northern hemisphere was sampled in far greater detail than the southern. The low-altitude coverage was primarily at the North Pole, which is why so much of MESSENGER's surface chemistry data focuses on northern regions, and why the polar ice measurements, while comprehensive, are much more detailed for the north than the south. And critically, MESSENGER's instruments, while groundbreaking, had limitations in sensitivity for certain elements. Lithium, for example, may have been present in MESSENGER data. Without being clearly identifiable against the noise, the detection threshold simply wasn't low enough. BepiColombo will not have the same constraints. Its orbit will be designed for more equatorial coverage, providing better global sampling than MESSENGER achieved. Its instruments represent a generation of improvement in sensitivity and spectral resolution. And it will operate through a longer nominal mission. The current plan calls for a mission of at least 1 Mercury year, about 88 Earth days per Mercury orbit, with the scientific mission running for multiple Mercury years to allow for systematic monitoring of how the planet and its environment change over time. The mission involves 2 orbiters that will separate and enter their own orbits once they arrive at Mercury. The Mercury Planetary Orbiter, built by ESA, carries instruments focused on surface composition, geology, atmospheric science, and magnetic field mapping. The Mercury Magnetospheric Orbiter, built by JAXA, is specifically designed to study Mercury's magnetic field, its interaction with the solar wind, and the charged particle environment. Together, they will provide simultaneous measurements from 2 different orbital positions, something that was not possible with the single MESSENGER spacecraft. This allows scientists to distinguish between global changes in the environment and local, position-specific effects, which is enormously valuable for understanding the dynamics of the exosphere and the solar wind interaction. The anticipation surrounding BepiColombo's orbital phase is palpable in the planetary science community. Scientists who have spent careers analyzing MESSENGER data, squeezing the last details out of a dataset that has been known for over a decade, are preparing new research questions that only BepiColombo can address. The list of open problems is long and substantive. Why is lithium escaping from Mercury's surface? What is the source of the elevated sulfur? How does the exosphere's composition and density change in response to solar storms? Are there surface regions that are systematically more chemically active than others? How does the southern hemisphere differ from the northern hemisphere in its exosphere contributions? Is the polar ice connected to the broader chemical inventory of the surface, or is it an isolated system? These aren't questions that can be answered from Earth. They can't be addressed by analyzing the existing MESSENGER dataset any further than it's already been analyzed. They require a new spacecraft with new instruments spending extended time in orbit around Mercury. And for the first time in more than a decade, that spacecraft is almost there. The broader context in which Mercury science now sits is one that didn't exist in the era of Mariner 10 or even in the early years of MESSENGER. The discovery of exoplanets has transformed the questions planetary scientists care about. When Mercury was being studied in isolation as the innermost planet in our solar system, interesting primarily in its own right, the questions it could answer were local ones. What is Mercury made of? How did it form? Why is its core so large? These are important questions, but they're questions about a single specific world. Now, with the knowledge that there are thousands of confirmed rocky planets orbiting other stars, many of them in orbits much closer to their host stars than Mercury is to our Sun, the questions Mercury can help answer have become much larger. Some of the most abundant type of planet in the galaxy appears to be the class known as super-Earths, or hot, rocky worlds. Planets larger than Earth, but smaller than Neptune, orbiting very close to their stars, in many cases close enough that their surface conditions would be even more extreme than Mercury's. Their proximity to their stars means they are being bombarded by the same kinds of processes that are stripping material from Mercury right now: solar wind sputtering, photodesorption, thermal desorption, micrometeorite impacts. If these worlds had atmospheres when they formed, those atmospheres are probably being eroded. If they have surface volatiles, those volatiles are probably escaping. The rate at which they're losing material depends on the same physical parameters that govern Mercury's material loss: the intensity of the stellar wind, the surface composition of the planet, the strength and configuration of any magnetic field, the planet's gravity. Mercury is our local, accessible, measurable example of this class of extreme planet-star interaction. Everything we learn about how Mercury loses material, the rates, the mechanisms, the spatial distributions, the temporal variability, gives us a framework for interpreting the exospheres and surface evolution of hundreds of distant worlds we will never visit directly. This is not a minor scientific contribution. It's arguably the most important long-term reason for the current intensity of interest in Mercury. The planet that was once ignored because it seemed to have nothing left to offer has turned out to be one of the most informative objects in the solar system for understanding the fate of small rocky worlds in general. Its chemistry, its escape rates, its magnetic field interactions with the solar wind, its shrinking interior, all of these are variables in a broader equation that applies to rocky planets across the galaxy. Mercury is our calibration point for that equation. And if the calibration point contains surprises lithium where there shouldn't be lithium, volatiles where there shouldn't be volatiles, dynamic processes where there should only be stasis, then the equation needs to be rewritten. That's the position planetary science is in right now. The equation is being rewritten. The old model of Mercury as a dead world is being replaced by something considerably more interesting and considerably more useful. A world that is actively shedding material, responding to solar input in real time, retaining volatiles against expectations, and still contracting slowly as its ancient core cools. This is not the inert reference point that textbooks described. It's a living example of the processes that shape and reshape rocky planets throughout their entire lifespan, not just in the first billion years. The irony is that Mercury's usefulness as a scientific reference point hasn't diminished. It's just changed in nature. Mercury is still a reference point, but instead of being a reference for what a dead planet looks like, it's becoming a reference for how rocky planets evolve under extreme stellar conditions, a template for understanding all those small, hot worlds that exoplanet surveys keep finding around other stars. The planet didn't change. Our questions did. And as our questions evolved, Mercury turned out to have the answers all along, waiting for instruments sensitive enough to read them. There is a particular kind of scientific moment that doesn't announce itself loudly. It doesn't come with a press conference or a dramatic image beamed back from deep space. It comes quietly, in the form of a number in a dataset that doesn't match what the model predicted, a spectral line where there shouldn't be one, an abundance that's too high, a detection that requires you to go back and check the instrument calibration twice, then 3 times, before you're willing to accept that what you're seeing is real. The discovery of lithium in Mercury's exosphere was that kind of moment. And it's the kind of moment that, in retrospect, often marks the beginning of a new chapter in how a field understands itself. To appreciate why lithium specifically is so significant, you have to understand something about the chemistry of the inner solar system and the assumptions baked into every model of rocky planet formation that has been built over the last several decades. The inner solar system, the region inside roughly 2 astronomical units from the Sun, where Mercury, Venus, Earth, and Mars formed, is supposed to be depleted in light volatile elements. The reasoning is straightforward and well grounded in thermodynamics. When the solar system was young, the region close to the Sun was hot, very hot. Hot enough that light, easily vaporized materials couldn't condense into solid form. Only refractory materials, heavy metals, silicates, compounds with very high melting points, could solidify and accumulate into planetesimals, and eventually planets in the inner solar system. Everything lighter and more volatile either never condensed there in the first place, or is quickly blown away by the intense radiation from the young Sun. This is why the inner rocky planets are dense compared to the outer solar system's gas and ice giants. It's why Earth has a large iron-nickel core and a silicate mantle rather than being made primarily of water and methane. The heavy stuff stayed, the light stuff didn't. Mercury, being the innermost planet, and therefore the hottest and most radiation-exposed region of the solar system during formation, should be the most extreme example of this trend. It should be the most depleted in volatile light elements of any planet in the solar system. More depleted than Earth, more depleted than Mars, more depleted than Venus. And yet, sodium was found in quantities higher than expected. Potassium was found. Sulfur was found in shocking abundance. Carbon was found. And now lithium has been detected actively escaping from the surface into space. Each of these detections chips away at the foundational assumption of volatile depletion in Mercury's surface. Together, they suggest that the story of how Mercury formed and what it's made of is considerably more complicated than the simple hot inner solar system model implies. One emerging hypothesis is that Mercury's surface was significantly modified after the planet formed. The volatile content of Mercury's surface may not primarily reflect the original composition of the material that accreted to form the planet. Instead, it may reflect billions of years of delivery from external sources, comets, asteroids, and interplanetary dust particles that brought volatile-bearing materials to Mercury's surface long after the planet had formed and cooled. If the flux of cometary and asteroidal bombardment in the early solar system was high enough, and if the chemistry of those impacting bodies was rich enough in light volatile elements, the surface of Mercury could have been gradually enriched in materials that were never part of its original composition. This isn't a fringe idea. The Late Heavy Bombardment, a period roughly 3.9 to 4.1 billion years ago, when the inner solar system experienced an intense period of large impacts, is believed to have delivered significant amounts of water to Earth and possibly to other inner solar system planets. If water was delivered in this way, lighter elements like lithium, sodium, and potassium could have been delivered along with it in the same impacting bodies. The question is whether the quantities delivered and retained would be sufficient to explain the abundances now being detected in Mercury's exosphere. The challenge with this hypothesis is that Mercury is very efficient at losing material. The same mechanisms that are stripping sodium and lithium from Mercury's surface today have been operating for billions of years. If material was delivered to Mercury's surface during the Late Heavy Bombardment, the radiation, sputtering, and impact vaporization processes would have been working on it ever since, gradually depleting it. The fact that detectable quantities are still escaping today either means the original delivery was very large, or the reservoir is being continuously replenished from deeper sources, or Mercury's surface contains these volatiles in mineral forms that are more resistant to desorption than the simple surface layer models assumed, bound more deeply in crystal structures that the surface processes access, only slowly. Another possibility that has gained traction in the wake of MESSENGER's surface chemistry findings is that Mercury's formation history was genuinely unusual, that it didn't form like a normal inner solar system planet at all. The most popular version of this idea involves a giant impact, similar in some ways to the giant impact believed to have formed Earth's moon, but with different consequences for Mercury. In this scenario, an early Mercury that was considerably larger and had a more Earth-like composition, with a significant volatile-bearing rocky mantle, was struck by a large impactor that blasted away much of the outer rocky layers, while leaving the iron core largely intact. The resulting stripped body is what we see today, a planet with an oversized core and a thin, depleted rocky shell. If this impact scenario is correct, the volatile elements currently present in Mercury's surface might be a mixture of the original pre-impact surface composition, partially retained in deep crustal rocks that weren't completely stripped away, and materials delivered after the impact by subsequent bombardment. The impact would have reset Mercury's surface composition in a dramatic way, but it wouldn't necessarily have driven every trace of volatile material off the planet. Deep pockets of volatile-rich material in the surviving crust could have remained, slowly being exposed and processed over billions of years of subsequent geological and surface weathering activity. A third possibility, one that cannot yet be ruled out, and that BepiColombo's measurements will help test, is that Mercury's interior is still contributing volatile material to the surface environment. The conventional wisdom is that Mercury's volcanic activity ceased billions of years ago, and that no significant outgassing from the interior has occurred since. But the discovery of relatively young pyroclastic deposits by MESSENGER explosive volcanic features that formed much more recently than anyone expected suggests that Mercury's geological history is longer and more complex than the old model assumed. If volcanic outgassing continued until relatively recently in geological terms, then some fraction of the volatile elements now present in Mercury's surface and exosphere could have been emplaced by late-stage volcanism rather than by external delivery. And if the interior is still warm enough to maintain a partially liquid outer core, it's at least conceivable that very small amounts of gas could still be migrating through the crust, through fractures and fault zones, contributing trace quantities of volatile elements to the near-surface environment. None of these hypotheses is mutually exclusive. The most likely explanation for Mercury's unexpected volatile inventory is probably a combination of all of them. Some original composition that was less depleted than simple formation models predicted, modified by a giant impact event, enriched by external delivery during the heavy bombardment, further modified by extended volcanic activity, and now being continuously processed and lost through the surface mechanisms that have been operating since the planet's surface first solidified. Sorting out the relative contributions of each mechanism is exactly the kind of problem that requires the detailed, spatially resolved, temporally monitored data that BepiColombo will provide. The water-ice story deserves its own extended treatment here, because it connects the volatile chemistry of Mercury to a question that resonates far beyond planetary science. The question of how water, and possibly the organic molecules associated with it, moves around the inner solar system and ends up in unexpected places. When astronomers first proposed, in the early 1990s, that Mercury might have water ice at its poles, the suggestion was met with significant skepticism. The idea seemed almost paradoxical. Mercury, the closest planet to the Sun, the hottest rocky surface in the solar system, harboring frozen water. The radar observations that first suggested it, showing anomalously bright reflections from Mercury's polar regions, consistent with the radar signature of water ice, were difficult to dismiss, but alternative explanations were proposed. Perhaps the bright radar returns were coming from some other material, some unusual cold silicate mineral or metallite compound that happened to produce the same kind of radar reflection. MESSENGER settled the question definitively. Its neutron spectrometer detected elevated hydrogen concentrations at Mercury's poles, consistent with the presence of water ice. Its infrared measurements showed that the polar crater floors were cold enough to maintain ice stability over geological timescales. Its reflectance data revealed that some of the ice deposits were covered by the dark, organic-rich layer that has since become one of the most intriguing aspects of Mercury's polar chemistry. The water ice is real. It's abundant, far more abundant than the minimum amount necessary to produce the radar signature that was originally detected. And it's sitting at the bottom of some of the coldest, most permanently shadowed locations in the entire inner solar system, 100 meters or more below the level at which any sunlight can penetrate. The dark organic layer on top of the ice is perhaps the most scientifically provocative aspect of the polar deposits. Organic chemistry, the chemistry of carbon-containing compounds, is not something that's usually associated with Mercury. The planet's high temperature, high radiation surface environment is destructive to organic molecules. Under direct sunlight on Mercury's equatorial surface, complex organic compounds would be broken apart by ultraviolet radiation in geologically trivial timescales. But in the permanently shadowed polar craters, the situation is entirely different. The temperatures are so low, and the sunlight so completely excluded, that complex molecules could persist for extremely long periods, perhaps for billions of years. The dark layer appears to have been emplaced at the same time as the ice, or at least from the same sources. The most likely scenario is that cometary impacts delivered both water ice and organic compounds simultaneously, with the organic-rich portion of the cometary material migrating to the polar regions, along with the water molecules, and accumulating over billions of years of such delivery events. Alternatively, some portion of the organic layer may have formed in situ through irradiation when high-energy particles from the solar wind and cosmic rays strike simple carbon and hydrogen compounds on the surface. They can drive chemical reactions that build up more complex organic structures. Either way, the polar craters of Mercury contain a chemical record of some of the oldest organic chemistry in the inner solar system, preserved in a deep freeze that has lasted since the early days of the solar system. This is relevant to the broader story of life's origins in a way that's worth spelling out. The organic compounds found in comets and carbon-rich asteroids include amino acid precursors, complex hydrocarbons, and other molecules that are building blocks for the chemistry of life as we know it on Earth. The delivery of these compounds to the inner solar system planets via cometary and asteroidal impact is believed to have been an important part of the chemical setup that eventually led to life on Earth. Mercury's polar deposits, if they contain the same classes of organic compounds found in comets, are a preserved record of that delivery process, a frozen library of early solar system chemistry sitting in perpetual darkness, waiting to be sampled. BepiColombo cannot land on Mercury and sample those polar deposits directly. It's an orbiting mission, not a lander. But its instruments can characterize the chemical signatures of the polar deposits from orbit with greater sensitivity and spectral coverage than MESSENGER achieved. And the data it returns will help prioritize what a future Mercury lander mission, a mission that has been proposed but not yet funded or scheduled, should target. The scientific case for eventually landing on Mercury's polar ice and drilling into that dark organic layer is compelling. And it will only get more compelling as BepiColombo refines our understanding of what's there. One of the most counterintuitive aspects of Mercury's current scientific status is how much the planet's proximity to the Sun, the very thing that caused it to be written off as a depleted, boring world, is now the source of its most interesting science. Everything unusual about Mercury, everything that makes it a productive object of study, stems directly from how close it is to the Sun and how extreme the solar environment at its orbit is. The intense solar radiation that was supposed to have stripped Mercury of all its interesting surface chemistry turns out instead to be the engine that drives the ongoing release of that chemistry into the exosphere, where it can be detected and measured. The solar wind that was supposed to have blown away any atmosphere Mercury might have had turns out to be one of the key mechanisms that continuously generates the exosphere from the surface material. The strong gravitational field of the nearby Sun that was supposed to have simply dominated Mercury's dynamics turns out to produce the most dramatic test of general relativity in the solar system, and to drive the eccentric, inclined orbit that gives Mercury its extreme temperature cycles and its bizarre solar sky motion. Even the polar ice, which exists because of the near-zero axial tilt that keeps those crater floors in permanent shadow, which is itself a consequence of the gravitational environment close to the Sun that tends to damp out axial tilts, is a product, in a roundabout way, of Mercury's extreme solar proximity. A planet at Earth's distance, with the same near-zero axial tilt, might not have permanently shadowed polar regions, because the Sun would be overhead at a shallower angle. Mercury's specific combination of proximity, tilt, slow rotation, and crater geometry creates the thermal conditions that allow ice to survive right next to the hottest surface in the solar system. This is the kind of systems-level thinking that Mercury increasingly demands. You cannot understand any one aspect of it in isolation. The exosphere is connected to the surface chemistry, which is connected to the formation history and the impact delivery of volatiles, which is connected to the solar-wind interaction, which is connected to the magnetic field, which is connected to the interior structure, and the still liquid outer core. The polar ice is connected to the volatile delivery history, which is connected to the bombardment rate in the early solar system, which is connected to the organic chemistry now preserved in the dark polar deposits. Everything links to everything else, and pulling on any one thread immediately starts to unravel others. This interconnectedness is part of why the current moment in Mercury science is so productive and so challenging simultaneously. BepiColombo isn't just going to answer isolated questions about the exosphere, or the magnetic field, or the surface chemistry. It's going to provide data on all of these systems simultaneously, and the most important science it produces will probably come from the connections between the different datasets, on the correlations and patterns that emerge when you have high-quality measurements of multiple systems at the same time, over extended periods, with instruments sensitive enough to resolve the fine structure that previous measurements could only hint at. The scientific teams preparing to analyze BepiColombo's data are acutely aware of this. The mission was designed from the beginning as an integrated scientific effort, not a collection of independent instrument teams, each pursuing their own narrow question. The two orbiters, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, were built to work together to provide complementary datasets that can be combined in ways neither spacecraft could achieve alone. The coordinated observations from two orbital positions will allow scientists to separate temporal changes from spatial ones, to distinguish between phenomena that are happening globally and phenomena that are localized to specific surface regions or magnetic field configurations. This level of scientific coordination is a significant advance over what was possible with MESSENGER, and it reflects how much the field's ambitions for Mercury science have grown since MESSENGER first began transforming our understanding of the planet. The question of what Mercury will look like in the far future, in the remaining billions of years before the Sun expands into a red giant and presumably engulfs the inner planets entirely, is one that planetary scientists are beginning to think about more seriously. It connects to the question of how Mercury is evolving right now, and whether the processes currently observed are stable, accelerating, or slowly winding down. In terms of material loss, the current rate of escape from Mercury's exosphere is gradual. The sodium tail, while real and measurable, represents a small fraction of Mercury's total sodium inventory per unit time. The lithium being detected is almost certainly being lost at a similarly low rate. If these escape rates remained constant over the remaining lifespan of the solar system, Mercury would not be completely stripped of its surface volatiles in that time. There's enough material in the surface and near-surface mineral reservoir to sustain the current escape rates for a very long time. But the escape rate is not constant, and it won't remain so. As the Sun slowly brightens over astronomical timescales, a gradual process that has been ongoing since the Sun entered the main sequence about 4.6 billion years ago, and will continue for another roughly 5 billion years. The solar radiation intensity at Mercury's orbit will, increase. More intense solar radiation means more efficient photodesorption, more energetic solar wind over the long term, and higher surface temperatures that increase thermal desorption rates. The exosphere will gradually become denser. The escape rates will increase. The rate of volatile depletion from Mercury's surface will accelerate as the Sun ages. The shrinkage will continue as well. Mercury's core is still cooling. The lobate scarps that record past contraction will be joined by new ones, not on any human timescale, but measurably in the geological record, if any future mission maps Mercury's surface in fine enough detail to detect the newest faults. As the core cools further, and a greater fraction of it solidifies, the convection driving the magnetic dynamo will eventually diminish, and the magnetic field will weaken. When that happens, the solar wind will have even more direct access to Mercury's surface, accelerating the sputtering rate and increasing material loss. The transition from a planet with a modest magnetic field to one with essentially none will be a significant step change in Mercury's interaction with the solar environment, and it's a step that is coming on geological timescales, not imminently by any human measure, but not infinitely far away either. By the time the Sun begins its expansion toward the red giant phase, several billion years from now, Mercury will likely be a world stripped to near-zero volatile content on its surface. The sodium and potassium and lithium that are still detectable today will be largely gone, lost to space over billions of years of slow, steady evaporation. The polar ice will be threatened not just by the increasing solar radiation, but by whatever changes occur in the shadowing geometry of the polar craters as the planet's interior continues to evolve. Whether any ice will survive into the far future of the solar system is an open question, but the trend is clearly toward depletion. What will remain is the iron core, the silicate shell, and the lobate scarps, a planet that has run out of everything interesting to lose, truly inert in every sense, waiting for the expanding Sun to finally absorb it. That final state is what the original Dead World model imagined Mercury to already be. The reality is that Mercury is not there yet. It's still losing material, still evolving, still changing in ways that are detectable and scientifically meaningful. The Dead World model was wrong, not in its endpoint, but in its timing. Mercury will eventually become what the model described. It's just not there yet, and the distance between its current state and that endpoint turns out to be much larger and much more interesting than anyone assumed. It's worth pausing here and thinking about what the story of Mercury's scientific reappraisal says about how planetary science and science in general works. The old model of Mercury, as a dead, inert, chemically simple world, wasn't the product of careless thinking. It was the product of careful, logical reasoning from the best available evidence. Small planets lose heat quickly, true. Planets close to the Sun should be volatile depleted, true, as a general principle. Mercury's surface looks old and cratered, like the Moon, also observationally true. The logic connecting these facts to the conclusion of a dead, inactive world was reasonable, given what was known at the time. The problem wasn't the reasoning. It was the incompleteness of the evidence. The instruments available in the Mariner 10 era couldn't detect lithium in Mercury's exosphere. They couldn't measure the sodium tail. They couldn't characterize the surface composition in the detail that reveals elevated sulfur and carbon. They couldn't confirm the presence of polar ice. They couldn't resolve the young lobate scarps from the ancient ones, or detect the evidence for geologically recent pyroclastic volcanism. The evidence for Mercury being more complex and more active than the Dead World model assumed was always there, encoded in the physics of the planet and its environment. What changed was not the planet itself, but our ability to read the evidence it had been leaving all along. This pattern, a model that seems robust based on available evidence being overturned by improved measurements, is one of the most common and most important in the history of science. Mercury's precession was a feature of the solar system for all of recorded history, but it only became a meaningful challenge to Newtonian mechanics when measurements became precise enough to quantify it accurately and rule out instrumental error. The polar ice was always there, but it only entered the scientific picture when radar astronomy became sensitive enough to detect it from Earth. The sodium tail was always streaming away from Mercury, but it only became detectable when ultraviolet spectroscopy improved enough to pick up the faint emissions from tens of thousands of kilometers away. What this means, practically, is that any planet or astronomical object for which our measurement capabilities have not kept pace with the complexity of the object itself is probably hiding surprises. Mercury had surprises hiding in plain sight for decades, waiting for instruments sensitive enough to reveal them. The lesson for planetary science, and for the way we allocate resources and design missions, is that declaring a world understood before you have the tools to read its full complexity is premature. Mercury is the most striking recent example, but it is almost certainly not the only one. BepiColombo's arrival at Mercury will mark the beginning of what many in the planetary science community are calling the modern era of Mercury exploration. Not because the previous missions weren't groundbreaking. Mariner 10 and Messenger both transformed the field, but because BepiColombo represents the first mission to Mercury that was designed with full knowledge of Messenger's discoveries. Messenger taught us that Mercury was surprising. BepiColombo was built to understand why. The scientific questions BepiColombo carries to Mercury orbit are sharper and more specific than those of any previous mission. The instruments are not generalist survey tools. They are precision measurement devices tuned to the particular questions that Messenger's data raised. The coordination between the two orbiters is designed to extract information that a single spacecraft simply cannot provide. And the duration of the mission, covering multiple Mercury orbits, multiple solar activity cycles, and multiple points in Mercury's eccentric orbit around the Sun, will allow for the kind of longitudinal monitoring that can distinguish between stable background processes and episodic events driven by solar activity. Some of the most eagerly anticipated measurements involve the spatial distribution of exosphere sources across Mercury's surface. Messenger data suggested, but couldn't conclusively demonstrate, that certain surface regions contribute disproportionately to the exosphere, that some areas are chemically richer in volatiles, or more exposed to sputtering, or positioned in ways that make their material especially susceptible to solar-driven release. If BepiColombo can map these source regions with fine spatial resolution, it will be possible to connect the exosphere's composition directly to specific surface geology, to identify, for example, whether the highest lithium release rates are associated with particular rock types or mineral assemblages, or whether they're concentrated around impact craters where fresh material has been excavated and exposed. This kind of surface exosphere connection would be transformative for understanding Mercury's composition. Right now, our knowledge of what Mercury's surface is made of comes from reflectance spectroscopy and X-ray and gamma-ray spectroscopy, techniques that measure surface composition indirectly and with limited spatial resolution. The exosphere, in a sense, is Mercury's surface talking to us directly, the planet literally broadcasting its composition into space in the form of escaping atoms. If we can map where those atoms are coming from, we're effectively mapping the surface composition with a technique that has complementary strengths and weaknesses to the direct surface spectroscopy measurements. The combination of the two will give a more complete picture than either alone. The magnetic field measurements from the Mercury magnetospheric orbiter will address questions that have been building since Messenger first confirmed the offset dipole. The cause of that offset, why the magnetic dipole is shifted northward by 20% of the planet's radius, is one of the most intriguing unsolved problems in Mercury science. Offset magnetic dipoles are unusual in the solar system. Earth's dipole is close to the planet's geometric center. Jupiter's and Saturn's are similarly centered. An offset like Mercury's is difficult to explain with standard dynamo theory, and several competing models have been proposed, each requiring different assumptions about the structure and dynamics of Mercury's liquid outer core. Distinguishing between these models requires detailed magnetic field mapping at multiple altitudes, which the two-orbiter configuration of BepiColombo is designed to provide. The interior structure measurements, building on Messenger's gravity field data with higher precision, will help constrain the size of the solid inner core relative to the liquid outer core, the thickness of the mantle, and the presence of any density variations within the crust that might be associated with volcanic intrusions or impact basins. These structural details will feed directly into models of Mercury's thermal evolution, how fast the interior is cooling, how long the dynamo will continue operating, and how much geological activity Mercury might still be capable of in geological timescales. And throughout all of this, the fundamental question about the lithium will be pursued. Where is it coming from? How much of it is there? How fast is it being lost? Is the lithium reservoir stable, or is it being depleted measurably on the timescale of BepiColombo's mission? These measurements will determine whether the lithium discovery was a fascinating anomaly or the first indication of a much broader revision needed in our models of how volatile elements are distributed in the inner solar system. There's one final dimension to the Mercury story that hasn't been fully appreciated in most public discussions of the planet's recent scientific renaissance, and it involves the concept of planetary habitability in its broadest possible sense. When astrobiologists talk about habitability, they usually focus on the habitable zone, the range of distances from a star at which liquid water can exist on a planet's surface. Mercury is spectacularly outside this zone. Its surface is far too hot on the dayside, and its lack of atmosphere makes liquid water impossible under any conditions on most of the planet. By the conventional definition, Mercury is one of the least habitable environments in the solar system. But the polar ice deposits complicate this picture in a way that's philosophically interesting, even if not practically significant for life as we know it. At the floors of certain permanently shadowed polar craters, temperatures are comparable to those found in the cold traps of Earth's upper atmosphere or on some ice-covered moons of the outer solar system. The presence of water, ice, and organic compounds in those permanently cold locations means that the basic chemical ingredients associated with life's origins, liquid water, and organic molecules, are present in close proximity, albeit not in liquid form, and not in conditions that are currently favorable for life. The organic layer on top of the ice is a chemical record of one of the most important processes in early solar system history: the delivery of water and organics to the rocky planets by comets and carbon-rich asteroids. Understanding that delivery process, its timing, its magnitude, its chemical diversity, is directly relevant to understanding why Earth became a living world. Mercury's polar deposits are a preserved record of the same bombardment that seeded Earth with water and potentially with the organic building blocks of life. Studying them tells us not just about Mercury, but about the conditions that made Earth's biosphere possible. That's a connection between Mercury science and the question of life's origins that rarely gets articulated clearly, but it's real, and it's scientifically important. The possibility that BepiColombo's measurements will inform a future lander mission to Mercury's polar regions, a mission that could sample the ice and the organic layer, directly represents one of the most scientifically compelling long-term prospects in planetary prospects. Exploration. The technological challenges are enormous. Landing on Mercury is extraordinarily difficult. Managing the thermal environment of a lander operating near Mercury's poles, where the crater walls experience direct sunlight and the crater floors are in permanent shadow, would require engineering solutions unlike anything currently available. But the scientific return would be extraordinary: a direct chemical analysis of some of the oldest, most pristine comet-delivered material in the inner solar system, preserved in a cold trap for billions of years. That kind of mission is speculative for now, probably several decades away at the earliest given the current trajectory of funding and technology development in planetary exploration. But the scientific case for it is being built, measurement by measurement, as BepiColombo refines our understanding of what those polar deposits contain. Mercury, the planet that was written off as a dead world with nothing left to offer, may ultimately be the location of one of the most scientifically profound robotic exploration missions in the history of planetary science. The story of Mercury, as it stands today in the second decade of the 21st century, is fundamentally a story about the limits of models and the importance of instruments. The dead world model was coherent, internally consistent, and wrong not because the scientists who built it were careless, but because the evidence available to them was incomplete. The planet was always more complex than the model suggested. The volatiles were always escaping. The magnetic field was always there. The polar ice was always frozen in those permanent shadows. The core was always partially liquid. The scarps were always recording the planet's slow contraction. None of this started happening recently. It was always happening. We just couldn't see it clearly enough until the instruments caught up. That's the central lesson Mercury is teaching planetary science right now, and it's a lesson worth taking seriously. The universe doesn't simplify itself for our convenience. Planets don't arrange themselves in a hierarchy from interesting to boring that conveniently matches our ability to study them. The most apparently featureless, apparently inert, apparently understood objects may turn out to be harboring the most unexpected science simply because their complexity exists at scales and in domains where our instruments haven't previously been sensitive enough to look. Mercury spent decades as the example of what a dead planet looks like. It's now becoming the example of what happens when you look more carefully at a world you thought you understood. The gases leaking from its surface, the lithium tail stretching into space, the magnetic field generated by a still liquid iron core, the frozen water, and organic compounds preserved in polar darkness, none of this fits the model. All of it is real, and the full picture is still coming into focus. BepiColombo is closing the distance. Its instruments are functioning. The team managing the mission is coordinating the scientific program that will be activated once the spacecraft reaches its final orbit. The questions are ready, the technology is ready, and Mercury, still quietly leaking atoms into space the way it has been for billions of years, is ready to be properly read for the first time. What the data will show is genuinely unknown. That's not a hedge or a rhetorical gesture toward humility. It's a direct acknowledgement that Mercury has already demonstrated more than once its capacity to overturn the expectations of the scientists studying it. The detection of lithium wasn't predicted. The elevated sulfur wasn't predicted. The young pyroclastic deposits weren't predicted. The magnetic field wasn't predicted. Mercury has a track record of surprises, and there is no particular reason to expect that track record to end now that we finally have an instrument suite sophisticated enough to look in detail at everything it has been trying to show us. The smallest planet in the solar system, the one that was supposed to have nothing left to say, is still talking. It has been the whole time. We're only now, finally, learning to listen carefully enough to understand what it's been saying. And whatever comes next, whatever BepiColombo finds in that exosphere, in those magnetic field measurements, in those surface chemistry maps, it will almost certainly be stranger, more complex, and more informative than anything the dead world model would have led us to expect. That much, at least, Mercury has earned the right to promise.